We're moving into the next chapter now, aqueous ionic equilibrium, and we're going to start with buffer solutions. And let me just warn you, we're going to get into some of the scariest and hairiest calculations of the semester when we're dealing with buffer solutions. Now, it's not that the calculations are difficult. In fact, you have done most of the calculations already. It's just standard ice table type of stuff. The problem is knowing what calculation you need to do. When you're reading through the problem and you see where you're at, which calculation do I need to do to get the answer? That's the hard part, because sometimes we're going to have to string 2 or 3 different calculations together to get the right answer, and knowing to do that is the difficult part. It's not the calculations themselves, it's knowing what calculation to do when. So pay attention to that while we're going through these problems. All right. So let's look at buffer solutions. These are solutions that resist pH changes because they have a mixture of a weak acid and its conjugate base, or a mixture of a weak base and its conjugate acid. Note its. So, for example, if you had CH3COOH as your acid, its conjugate base is CH3COONA. Now, sodium is just a spectator ion, so it could just be CH3COO minus. But if you have acetic acid, the conjugate base of that, its conjugate base is acetate. And note, the conjugate base and the acid must be in greater concentration than you normally find from dissociation. So if you just throw, you just throw acetic acid into water, you'll have acetic acid and a little bit of conjugate base due to dissociation. That's not a buffer solution. A buffer solution would rise if you threw in extra acetate ion. All right. So there's one buffer solution, HF and F minus. Is that a buffer solution? Is that a weak acid and its conjugate base? Yes, so this is a buffer solution. How about H2CO3 and NaHCO3? You mix those together, is that a buffer solution? Well, is this a weak acid? Is this its conjugate base? Yes. Okay, this is a buffer solution here. How about CH3OOH and F minus? Does that make a buffer solution? Is this a weak acid? Yes. Is F minus the conjugate base of this weak acid? No, it is not. So this is not going to be a decent buffer solution. And let's just throw one more in there just for fun. How about HCl and NaCl? Is this a buffer solution? No, it's not. Why is it not a buffer solution? Because HCl is not a weak acid. HCl is a strong acid, and although NaCl is the conjugate base, it's not the conjugate base of a weak acid. So that's not a buffer solution either. You need to have a weak acid and its conjugate base. All right. And the thing about these buffer solutions, they can resist the pH changes because when you have a weak acid and its conjugate base, both in appreciable amounts, if you add base to that solution, well, the weak acid will neutralize a lot of that base that you add. If you add acid to that solution, well, the conjugate base will neutralize the acid. So the pH won't change because the added H plus or the added OH minus can get taken away by the acid and its conjugate base, whichever one is appropriate. Okay, there are several ways to make buffer solutions. The easiest one is just take a weak acid, or excuse me, to make ways to make them one, mix the two solutions, take a weak acid and a solution of its conjugate base, aqueous, mix the two together. So take like 0.1 molar acetic acid and 0.1 molar sodium acetate, mix those two solutions together, boom, you got a buffer. Another way to do it is add sodium hydroxide to aqueous weak acid, but not enough to use up all of that weak acid, because sodium hydroxide will react with the weak acid to make water plus the conjugate base. If you don't add a lot of sodium hydroxide so that you still have a bunch of this weak acid around, then you'll have this weak acid and you'll have some conjugate base made by the sodium hydroxide, all in greater concentrations than from dissociation, so then you'll have a buffer solution. All right. Now, calculating buffer solution pH. We'll go through 2 ways. The first way is ice tables. This is just a regular dissociation. The difference is Le Chatelier's principle comes into play because we have a common ion. Later in the book, we'll discuss a little more of the common ion effect. So let's go through an example. Calculate the pH of a buffer solution that consists of 0.1 molar acetic acid and 0.2 molar sodium acetate. All right, well, little aside here, since we're going to need ice tables, we'll need to know the Ka value. The Ka is 1.8 times 10 to the minus fifth for acetic acid. All right, so now in order to have an ice table, we must have a reaction. Well, what reaction occurs whenever you have acetic acid? Well, acetic acid plus water is in equilibrium with H3O plus and acetate ion here. You have to have some reaction. You have to have a reaction that has the acid and its conjugate base in it, and the easiest reaction is just the dissociation of the acid into H plus and the conjugate base. All right. Ice table, initial change equilibrium, have 0.1 molar acetic acid. Before any reaction happens, we don't have any H3O plus, but note we put in 0.2 molar acetate. So this is our common ion. We have some acetate in there. Now, Le Chatelier is going to tell us that if we start with some product already there, then this reaction won't happen as much as you think it would. You already poured in some products. So Le Chatelier says if you just had acetic acid, it had dissociated like this. You put in some product, it will kind of reverse and head more towards the left to try to get rid of this. So this common ion, putting it in to begin with, is going to stop the formation of H3O plus more than just dissociation would. All right, so we have our 0.2 molar acetate. Since we don't have any H3O plus, this reaction can't go backwards until we make some, and so we have to make some. This will be minus X plus X plus X, 0.1 minus X, X, and 0.20 plus X. Standard ice table stuff we know right now. At this point, we have to plug in to our equilibrium constant expression, our Ka expression. And so let's look for that. And we have, here it is, we know Ka equals concentration of H3O plus times concentration of acetate divided by the concentration of acetic acid. Plugging in our numbers, our 1.8 times 10 minus fifth. Note we've got X. We got 0.200 plus X and 0.100 minus X. Because on the previous page, we had the 0.200 plus X for the concentration of acetate, the 0.1 minus X for the acetic acid. So those are the values that we plug in to this ice table, or to the Ka expression. And, oh, this is looking nasty, but remember how we could ignore this minus X here? Because this value of Ka is very small, and this is 0.1 or so we can ignore the minus X. Can we also ignore this plus X? Well, yeah, for the same reason, because X is going to be very small compared to 0.2, so we can ignore this plus X. And all of a sudden, this math becomes easy. 1.8 times 10 to the minus fifth equals X times 0.2 divided by 0.1. So just take 1.8 times 10 to the minus fifth, multiply by 0.1, divide by 0.2. You have X equals 9.0 times 10 to the minus 6. Now that's our concentration of H3O plus from our ice table. So if pH is a negative log of 9 times 10 to the minus 6, pH is 5.05. Not a problem there. But when it comes to buffer solutions, when you have these acid and bases, conjugate bases in appreciable amounts, Henderson and Hasselbalch came about and they said, let's do a little bit of derivation here. Let's do some math. And what they said is, okay, let's look at this equation. HA, our acid, is in equilibrium with H plus and A minus. Here's a Ka expression, no issues there. Just rearrange this, solve for H plus. Well, that'll just be Ka times the concentration of HA divided by the concentration of A minus, just solving this for H plus. And then they said, let's take the negative log of both sides, because if we have H plus here, the negative log of H plus is pH. Well, if you know your rules of logs, if you have something times something and you take the log of that, that means it's the log of this plus the log of that. But we're taking the negative log. So the negative log of H plus equals a negative log of the Ka minus the log of the concentration of H plus over A minus. Now, if you have a negative log of something, you can actually turn it into the positive log if you flip over these two things. So let's take AHA from the top, put it on the bottom. Let's flip those. So now we've got the negative log of H plus equals a negative log of Ka plus the log of the concentration of the conjugate base divided by the concentration of the acid. Well, recall pH is negative log of H plus. So negative log of H plus is pH. The negative log of Ka is pKa. So this little p kind of means negative log of. pH, negative log of H. pKa, negative log of Ka. Which means this expression boils down to pH equals pKa plus log of concentration of A minus divided by the concentration of HA. This is the Henderson-Hasselbalch equation, and this will save our bacon a number of times when we're doing calculations. And note, this Henderson-Hasselbalch works as long as we can take our little shortcut, as long as our concentration of acid original minus X is essentially the concentration of HA. As long as we can do this, getting rid of the plus X or the minus X here, as long as that is valid because of this value of the Ka or Kb, then Henderson-Hasselbalch equation will hold. You may recall from most weak acids or weak bases, Kb's, the numbers are smaller than 1 times 10 to the minus fourth. Therefore, this works out the majority of the time. Okay, so let's use this equation now. Instead of going through the ice tables, let's look at something because we're going to see some happy stuff here. Remember our previous buffer solution. We had 0.1 molar acetic acid, 0.2 molar acetate ion. The Ka is 1.8 times 10 to the minus fifth. You just take the negative log of that, you get the pKa, that's 4.74. So then the pH is just going to be the pKa, 4.74, plus the log of the amount of A minus, the conjugate base form, which is 0.2 molar, divided by 0.1 molar. So just take 0.2 divided by 0.1, take the log of it, that's a log of 2, pH equals 4.74 plus 0.3. And I worked it out longhand, which works out to pH equals 5.05. And note, that is the same pH we got when we went through that whole ice table. So note, with Henderson-Hasselbalch, you don't have to go through the ice table. Just as long as you know the concentration of the acid form and the base form, plug them into this equation, boom, out comes a pH. Gotta love Henderson-Hasselbalch. All right. So that's the introduction to buffer solutions. We will, in the next video, go through how to do some calculations. We just introduced basically how to do it, but we'll go through your thinking process. How do you know which calculation, what equation, what math you need to do when? We're going to go through that in the next video.